This is for EEE 4304 lab. My name is Ricardo Sandrea. My Panther ID is 5721986.
And I'm Aldo Langonyani. My Panther ID is 3849252. This is our circuit. So this is the static electricity detector, and this is just the smaller version of it, as you saw it light up.
Different configuration, possible design for it.
Okay. So yeah, if you just, the whole point is that if you just touch that wire there, which is like the antenna, it just lights up the LED because it detects static. It has there's 3 BJTs. There's a 1 mega ohm, 100K, and 220 ohms. That's the 9-volt battery. And the smaller one is just a BJT with a 1 mega, right?
Yes.
Oh, sorry, that's 100K.
That's the 100K.
Yeah.
Yes, the 100K. No. Yeah,
it's 100K.
We tried the 1 mega, and you can see that it lights up, but it's not as good as this design. You can see a slight flicker in there. So the body acts as like a conductor, in a sense. The static is just the buildup of charge, the imbalance of it. And this is very important to have when you're dealing with important resources and materials and expensive equipment. You want to have a good way to detect static and try to mitigate its effect on your circuit and on your electronic devices. So here's my deck. This is running. It's across the LED, and you can see the effects of it. So
that's when it detects static, we're just simulating the static by just putting our finger directly on the wire.
So this is me taking off my finger,
and it goes back to.
And it's just your normal diode, and then right there.
This is just showing that you're getting an AC signal, because the input, even though it's 9 volts DC, it's being rectified by the LED, so you're getting an AC output.
So right there you get, once you touch it, it becomes DC output. It stays constant at 1.9 volts, almost 2. Okay, so right there.
And then it just goes back to when you do it. And then the multi-sim, let me just do that.
Yeah, with multi-sim.
Right, so this is just our circuit multi-sim. You're just getting about 3.5 volts across the LED from just this configuration, and then the switch is where the loose wire is, where we just touch it and then it lights up the LED. Right. So this is this is an important project because there's a lot of problems with static. So for example, there's a lot of gases that ignite when with enough electricity. So it's good to have a static detector in the workplace, especially industry, like industrial places, because if there's a gas leak that you wouldn't know about because there's odorless gases. So if you have a static electricity detector, you could just detect that, and there's static there, so you won't blow up if you light something up in that place. There's also a lot of applications for underwater use. So if anything ever, like while you're doing underwater welding or something like that, if there's ever a leak in the system or anything like that, the wire's going to get into the system, and it'll just run across the static electricity detector, and you know that there's a leak in that specific sector.
There's also an entertainment sense of application to this project. There's many different what they call EMF or ghost detectors that they use. This similar design in which static is supposed to be when there's static or what they call ghosts or something like that, something abnormal is caught, then the LED would light up, and then the equipment that they do have is used for kind of just shows in general for that. So that's one other application. Not as serious though.
There's a big issue with printed circuit boards. So they're very sensitive to electrostatic, to static. You can completely burn up the entire PCB with just very little bit of static. That's why people usually have like grounding straps or anything like that when they work with them, or they're soldering them or just taking them apart or anything. There's people always wear the straps, because even I think it's something like 1,000 volts of static, which is very easy to build up. You usually get about 15K just from like rubbing the carpet. So it just does, you can completely burn up an entire PCB. So yeah.
And it's good to have these safety precautions to avoid that. Equipment costs sometimes like over thousands of dollars, and a little charge like that anyone can just, any equipment has a malfunction, you touch it, something like that happens, and then that's it, all that money lost. So companies have to invest money into not having to then replace all these machines later on.
So one other thing about our circuit is that modifying these values of the resistors will give it more sensitivity to different levels of static. So if you're just getting lower values, then it's more sensitive to just any static in the air, versus very high values of resistor, which will make it very hard to detect some static. So on that topic, when we were doing the proposal, I found this device that was being used, which was this electrostatic sensor. And what it is the problem with this was that it had to be connected to a power supply at all times, where our system is just a very simple robust system where you can just use any battery and it can be used to power just a simple small sensor, versus something like this which has to be plugged in the entire time. And even though it has a very large coverage, ours can be specifically tailor-made to any specific amount of static that people are worrying about, depending on what work is going on. Anything else? Actually, do you want to go over like what you saw in the smaller circuit they have there?
This right here?
Yeah.
No, this talks about how in this circuit right here, the BJT or a MOSFET, which could also be used, is used as a basically on and off switch. When it comes in contact with you, then it turns on. Right here, again, it's a very small light. If we were to change the resistor value, or even the different BJT or MOSFET device, we'll get either brighter or even dimmer. It's already pretty dim, but we can get it to be brighter. Also, the experiment uses a different battery, which could affect that. This one's 9 volts, and the application here only has the 6 volt battery one. But depending on, we can always change the values of this and accommodate for the 9 volt as need be. Just right now we're limited with the MOSFET and the BJT devices that we have.
Let me just show one thing. That this here, the battery, is being fed to the LED and the resistors. The battery, the 9 volts, is in parallel with all of these resistor values. And then, for the most part, other than this part here with the base here, all the collectors collected to the other base of the other BJT and so on until this one is finally grounded. And then this one, the base isn't connected to any collector. It's just on its own, this is where the trigger is to light up the LED from static detection. And this one just obviously has a very similar design.
It's the same exact design, except instead of having 3 by parallel, we just have one by series. It's connected to the gate. I mean, you can see that clearly. It's connected to the LED is connected to the drain, and then the ground, the emitter is grounded here to the battery, just fed here. And that's it. It's a shorter version of this bigger one, but you can see the benefits of having the bigger one in this case, in this scenario, which is more sensitive than this one, as this one only gets a very small flicker.
Yeah, very reflective, yeah. And let me see. Okay, so for the cost, let me just explain. So right now what we're showing you, there has 3 resistors, but you can also have a potentiometer to again just vary it around. The 3 MOSFETs, but in this case we're actually using BJTs. They work better than the MOSFETs from our testing. And this is just the proposal part. This is what we actually came up with. Without BJTs ended up working better. And see, so for the most part, we saw the battery would be the most expensive part of the circuit in the rheostat then. So we're saying $4 for the battery, $3 for the rheostat, and the rest of it is just about cents, the resistors, the wiring, everything. So you end up getting a cost around $7 to make something like this. What else? So it's just methodology and some references we used for the, yeah. Anything else?
Sources say that there's other ways to get rid of static electricity, but some of these are just not available. You can't always rely on these methods. For example, they say the low-tech way to remove charge fully from an insulator is to dip it into ground or grounded water, for example, breathe on it. But with this, you can just detect it and fix it, because first you have to have a way to detect it. It can happen essentially anywhere, so this is a very good device to set up when you know that it's going to happen, and it can be very harmful to the setup you have or the environment you could essentially mess with. So it has multiple applications to that. It's pretty much
right.
what it is.
Right, I think we're done. So that was it. Thank you very much for your time.
Thank you.
And this is just the final project to look at it again, and that's it.